Welcome to 331 Analyzing Address Resolution. So, we're going to learn how Resolution Protocol works, ARP, using a lot of Wireshark stuff. So, a little bit of intro before we get to the lesson. Oh, why did I just hit that button? Okay. Anyways, so analyzing the network traffic. A few things that I think are important in this. There's a lot of background here, but reminder that previous lessons when you use Wireshark, we had the idea of packets. So packets are the chunks of data that are transferred over the internet when two computers need to communicate, whatever. Sometimes we're breaking if we want to send a big message or a big picture, we break it into a bunch of smaller packets, right? And now packets are kind of so networks exchange IP packets that are often called packet switched networks. Everything is packets going around. So when we're doing Wireshark, we capture those packets to see the information going around. You're like, wait, someone can actually just see all the network traffic happening if you run Wireshark? Yeah, basically. But a lot of times it's encrypted, so they don't know everything that you do, but as long as the information's encrypted, they can. Yeah, I don't know. Try it out at home. Go to a Starbucks. Put Wireshark on your computer, load into the Wi-Fi network at Starbucks. Just watch the Wireshark traffic fill screen. Most of the internet. So we have this OSI model. If you ever want to sound smart, like cybersecurity, say OSI model. It's our structure for how information is structured on the internet, how it transfers, right? The different layers of the network. So you have your data layer, like is the applications being used, session you logged into. But then we have this transport layer right here. And the transport layer, well, let's back this out. We have our physical layer down here. This is actually your cables, your hardware in here. That's the physical layer of the network interface. Then you have the internet, how things communicate with each other, and the packets sent. Now, in those packets, we have different types of we transport different types of information. We have TCP, UDP packets right here, and then those packets are used for data for applications. Things that might be useful for you: TCP versus UDP. TCP is like traffic that needs to always arrive like 100%. Like for example, if you are going to a web page and you want to read a news article, let's say, or you want to go order a sub sandwich at John Smith Subs this weekend for the fundraiser. You want this whole website to load up. Like, what if these picture doesn't load up or some of these menus don't load up? Then the web page doesn't work. That's not good. So when stuff's transferred, sometimes all the packets don't make it, and they say, "Hey, send that packet again." Okay, we make sure it's 100% inaccurate, and just keep doing it till it is. Now, UDP traffic. Sometimes there's traffic that doesn't need to be accurate all the time. It just needs to keep running fast, like live streaming, right? Oh, what happens if they miss a frame or the sound glitches a little bit, doesn't get the whole sound transferred over. You say, "Oh, wait, I have to stop the live stream." No, you don't. You go, "Oh, you just hear a little glitch and we just keep moving on." That's UDP traffic. Streaming stuff. We just got to keep going fast. So different types of traffic have different standards of completion. And there you go. So address resolution protocol. So that's what this whole lesson's about. Now, the idea is that I'm going to skip some of this because that was confusing to me. I like these picture parts. Here's address resolution protocol. You're sitting there on the network. It's about connecting the MAC address of machines with their IP addresses. So you're remembering which MAC address is, if I want to send information to a certain IP, oh, it's this MAC address back and forth. So computers keep track of an address resolution protocol. We have this address resolution protocol, or ARP cache right here. So let's say if your computer C here, we're going to define them by their MAC address. That's the physical address. That's like the address of their network card for the computer. You can think about the actual computer is the MAC address. The IP is kind of like where it's at on the network. So it keeps a record and says for IP address Y and Z, well, Y has a MAC address of B, and for IP address Z, you go to the MAC address A. So it knows those two things, right? So the Z is going to be this router right here, and then B is this other server on the network. Okay. Now, ARP allows you to update this table, and it's how we keep records of this. So here's how they update. Let's say this computer says, "Hey, I have to go to this IP address W. But I don't know where it is." So it sends a message to the network, and it broadcasts this message. It says, what is the MAC address of the system that owns IP address W? Sends it to the switch, and then that MAC address goes to every machine on the switch. And then, goes, hey, I'm MAC address D. I have that IP address, and it'll send the message back. So broadcasting the message out, get the IP address, and then coming back in. Says, oh, that's me. And then as soon as MAC address C gets that, he updates its table, says IP address W is MAC address D. That's one way that ARP can work. So it keeps a track of this. And this way that this guy can now communicate with via MAC address when it ever needs to connect to this computer for whatever reason to send a message to it. Now, another way you update the ARP cache is computers will just broadcast and say, hey, I'm new here. I'm MAC address E. My IP is V, just to let y'all know. So they'll send that message out to the switch, and then that just switch will send it to all of the computers out there, and boom, you have and these computers will update their cache. So all the computers in that second step will just update their cache after getting that message. Those are ways to update that. It's like you're new to the neighborhood. Go, hey, neighbor, you walk door to door and say, well, hello. My name is Brophy. I live at this address. Nice to meet you. And they go, oh, hi. Okay, I'll write that down. Now, we're going to analyze what both those methods look like as network traffic in this lesson, and how hackers could potentially exploit this type of traffic. So I launched my lab. It's already open right here. I'm going to do step number 2. And step number 2, we're opening activities 331. So activities, 331 files. Let's open up one first. Resolution. This is going to be the first method where we had this guy has a question, and then like, who is this one? And then the one he was looking for responds. It says, oh, that's me. Okay. We open up resolution. Hey, I have 2 packets in here, only 2. They're kind of filtering this out for me. So we have, notice this. Now we've done Wireshark before, so we can look at this. The first thing is a broadcast. So it's info right here kind of tells you what's happening. And then you have your source and destination. So source is this MAC address right here, Han Hai Per. I think that's a computer on the network. So that's some computer on the network. And destination is broadcasting. So what broadcast does, sometimes you have a source and destination MAC address when I'm sending things. But in this case, it says, broadcast says, hey, send it to everyone. So it's broadcasting it to the world. And the protocol is ARP protocol. And then what it's saying is, who is IP address 192.168.0.1? Please tell IP address 92.68.0.14. Which is probably this computer itself. So it's saying, hey, who has this? Can you tell whoever that is? Please tell me. It sends that out. Then D-Link, which that's the IP address of the router for the network. The D-Link router says, hey, I'm 92.68.0.1. My MAC address is this thing. And it sends it directly back to the Han Hai Per. Right? So that's what we're doing. There's our 2 packets as messages right there. All right. Okay, so that was kind of step 3 right here. Let's type some information here. So expand the frame entry in the packet details pane. Record some of the packet details. So let's do packet 1. So packet details pane is right over here. I'm actually going to expand this a little bit. I want to do full screen because it kind of messes up. So we're going to do frame. If you remember, right here is the frame details. I'll make this a little bit bigger. Hopefully you can see it. The arrival time of the packet. So we can click on expand frame. You can see arrival times December 10th, 2006. Old. This time here. So one thing, I'm going to give you a hint. If you want to see, this is the actual time of the computer or of whatever the machine Wireshark's running on. But if you want to see like relative times, I think this number tells you a lot here. So I'm actually just going to I'm going to break the rules and write this number. This is at time 0. So 0.000. That's what I'm going to write down. I'm going to say my arrival time is 0.000. The frame length. Your frame length is 42 bytes, which is also right here. So we can call it 42. And the protocols in the frame. So you're like, what are the protocols? Protocols in the frame are Ether type, and ARP. Okay. So I'm going to write those down. Okay, I can lose track. So ether type and ARP. Okay. I don't really know what I know ARP is. Okay, cool. Expand the Ethernet 2 entry in the packet. Record the values for the source and destination address. You go to Ethernet 2, you can get the source and destination, which are actually up here too, right? So these details in these columns, like they're just, this is the same information can be found down here. Your source is Han Hyper 6E8B24 or this whole MAC address. I'm going to do it as this ASCII format here, this Han Hyper 6E8B24. So on Hyper 6, I already forgot. 6E8B24. 8B24. And the destination, this destination was broadcast with all Fs. So I'm just going to say broadcast. And all Fs. What's the format of these two? These are MAC addresses. Okay, but it's kind of like this pseudo MAC. This like half of this is a MAC address, half is like kind of this name for it because it knows the name. Kind of like a shortcut. And the MAC address for the broadcast is all Fs because that's the special MAC address for broadcast messages. We did that probably in Unit 2. Okay, so expand the address resolution protocol entry in the packet details pane. Record the values. So ARP right down here. We record these values. So the first one, the protocol type. We're going to do protocol type is IPv4. IPv4. If you don't know what IPv4 is, you can look this up. IPv4. And internet protocol. This is just, these are like the rules to transfer our packet rules, transfer packets across the internet. We follow these rules. IPv4 has been around since the 80s. There's been, you might have heard like talk about IPv5, IPv6 and stuff. People like, oh, let's replace this to have a better one. But the problem is like, and everyone needs to do it. It's like switching to the metric system. We don't do that in America. You need everyone to switch. Otherwise it gets confusing. So it's hard to just switch a few of them. Opcode. Opcode is going to be a request right here. So request right down here where it says 1. So I'm going to say request. You can write 1. Sender source MAC address. So the sender MAC address is Han Hyper. So I'm just going to copy this again. Sender IP address would be 92.68.0.114. 192.168.0.114. 192.168.0 is typically like those internal network type things, and this is whatever computer number on that. Target destination MAC address is all zeros, so I'm going to just call it, I'm just going to call it broadcast. And then the IP address for the broadcast is 192.168.0.1. 168.0.1. Why does it say the IP address if it's just broadcasting? Why does it have that IP address? I think it talks about it somewhere in the lessons. I mean, that's the address of the router. Oh, it doesn't talk about that. That's weird. Okay, why is it all zeros? Because, oh, wait a minute. Yeah, why is the target all zeros for the MAC address? Oh, it's not broadcast. I should just said zeros. Why is it all zeros? Because there is no MAC address. You're just broadcasting it, right? So it serves as a placeholder. There you go. Now I'll use the packet bytes pane to observe a byte review. Okay, so this is kind of neat. So what they're saying here is, you know how we click things around here? Notice down here, this is the hex dump area. These are like, this is hexadecimal base 16 math. So whenever you click on things right here, like I'm going to say my type is ARP, right? Or Ethernet 2 or the destination broadcast. Notice it highlights, this is Fs. It highlights these Fs right here. So when we're actually sending the packet, like this is the raw data, you can think of it that way. But over here in this details pane is like, depending on what's that data is and the location of that data is how it translates to the rest of this stuff. So the first hex is base 16, so it goes 0 through 9 and then A through F, right? So the first 2, 4, 6, 8, 10, 12 characters are going to be the destination broadcast, destination MAC address every time. The next, 6, 12, it's 12, right? 2, 4, 6, 8, 10, 12. The next 12 are going to be the source MAC address, and then so on. So then the next part's going to be the type of protocol or the type, whatever, right there, and then so on. Whenever you click, like even this protocol right here, that's where that information is going to be. Get the MAC addresses. Notice how it highlights. So, but this is hard to read human eye. That's why it translates up here. That's the point of seeing that. We can see where those MAC addresses and all that those numbers lie. Click the sender IP address and compare the values the packets pay in the packet bytes. They should be the same, right? So if I do my sender MAC address with 016 blah blah blah, the same thing up here. So that's the idea with this hex dump. Raw data. Let's look at the details of the reply packet next. So that's packet number 2. Click on this. In the reply packet, we're going to frame details. What's the arrival time? Now, you can look at this arrival time right here. But this, I like this number right here. This tells you the difference. So this started at like time 0, the beginning, and this is time 0.004. So 4 thousandths of a second later. So super quick for us. I'm going to say 0.004-ish. So it replied after there. 4 thousandths of a second later. The frame length is going to be 46 bytes. Protocols. Ether type and ARP. Okay, so ether type ARP. Done. Compare the reply data to the request packet. Verify the protocols match. And the reply arrival time is after the request of arrival time. What are the possibilities for arrival times? Okay, so it's good to look at arrival times because you might notice, like, what if that packet, you want to make sure the reply appeared after the broadcast, right? So if you saw the reply was happening before the broadcast, you might be like, wait, someone's doing some funny business. Or maybe if you saw that reply happen way after the broadcast, you also might be like, something might be going on our network. Now, how do you know that this distance right here is not too far? I think that comes with experience. Like, is that appropriate time or is that too long for something like that? I don't know. It comes with experience. So you can watch those travel times and see if things are happening too quick, too slow, whatever, out of order. That's why arrival time is important. Necessary, expand the Ethernet entry. Let's add this. Okay, so get the details right here. Our source and destination. Our source was D-Link and destination was Han Hai. So it's kind of the opposite. Our source was D-Link. Oh. So the D-Link, which is our router, so we're going to call it D-Link OB22BA. D-Link OB22BA. I think it's actually 0B. Yeah, there's no O's. It's all hex. And the destination is the Honhaiper. I don't know. I wonder what. So D-Link is a brand of router. I don't know what Honhaiper. Is that like a computer brand or a server brand? I don't know. I don't know what that's like a shorthand for. They have said like Dell or something or Hewlett Packard, like it does Hewlett later. Like, oh, that's probably like a Hewlett Packard computer or printer or something. I don't know. I don't know what this is. So the reply destination address matches the broadcast source address. So notice the source and destination, or the destination for the reply should match the source of the previous packet. And I know we wrote those down, but you can also see it like, source and destination. Those are matching. Necessary, expand address resolution. Let's do the rest of this. So IPv4. Or is it on this one? The protocol, the reply. This is going to be a reply opcode. Reply, and that's a 2. Sender MAC address. So sender is the D-Link right there. The sender is this D-Link address. And the sender IP is 92.68.0.1, which is our router's address. And the target is going to be this destination, right? Han Hyper. The IP address for that is 92.68.0.114. So how are the opcodes related? Well, okay. So this is the reply to the other's opcode of 1. So opcodes are just kind of telling you what type of message we're trying to send between the two. And there's the whole system of receiving, requesting, acknowledging, blah, blah, blah. That's done that before. That's not going to be matter too much for today at all. It don't matter at all today. What's the sender MAC address value, and where does it else appear on Wireshark? So the sender address, MAC address, is going to appear in the source. So it can, in the source column, it's in the source value. So in Ethernet here, we had this. And then you can also see it down here in the hex dump as I highlight that. Consider a situation where sender MAC address doesn't match the host sending the reply. What might this indicate? So the sender's MAC address doesn't match that of the host sending the reply. Okay, depending on the implementation, the requester might accept the spoofed response. So the sender's MAC address doesn't match that of the host sending the reply. Okay. So, if you had, when we wrote things down here, the target and the target MAC address. So what if the sender's MAC address and the IP address didn't match up? Like this sender MAC address and the source IP address, what if those didn't match up? Like those should, right? But what if they didn't? You're like, might be suspicious. All right. So that's just that basic one. We're sending one message out, broadcasting, and we get the reply from the person who said it. Now I want to try a different one. We're going to open up gratuitous. This is the case where this is the case where you're just broadcasting to the world. You go, hey, I'm this address, and then everyone else updates. So we're going to see how this gratuitous message. Gratuitous. Actually, that's a negative word. Is that? But I don't know if that. Okay, sure. So we're opening up this one. So what does that traffic look like? We're sending one message to the world, and then it's just being spread out to all the computers. Okay, so we got one packet. Now they just to simplify, it's just this one packet, the broadcast message. All right. So explore the packet details. Which packet detail entry does the IP address? Where's the IP address in this? If you remember, you go to the address resolution protocol. You can see the senders and the target IP address here. Senders IP address and the target IP address. Why are those the same? I think because we don't have a target because we're just sending it out to the world. So in the ARP entry, what's the sender's IP address? It's going to be right there, 24.6.125.19. What's the address in hexadecimal? Okay, what's cool here, this is the IP address in decimal numbers 0 through 10. Notice how it highlights different numbers down here, 18, 6, 7D, 13. That's it if you converted it to base 16 math. But it doesn't matter for us right here. But that's just showing you where it is on the hex dump. That's why those numbers don't match up, because this is base 10 decimal math, what we're used to, numbers. And then this is base 16. I know. ARP is an efficient way to leverage layer 2 networking so that packets in layer 3 are efficiently routed through the net, but it's also very trusting. Like, hey, yeah, if I just broadcast and say I'm this person, you just got to believe me. And like, see all these messages, we're just saying that, oh yeah, I'm this person. Oh yeah, okay. Just trust it. But that trust can be dangerous. The router takes this replies it receives as is, no authentication or validation occurs, and the ARP check where the host really owns that IP address. Maybe I'm just lying. And this is how you can exploit things. So here's a diagram. You have this computer wants to talk to the router between the switch. Okay, send a message, receive a message, right? Oh, but I want to talk to the router. Now this guy comes in the middle and says, "Oh, I'm the router now. Just talk to me. Just talk to me." So now he's kind of changed how information. This computer's instead it's talking to him first before it actually goes to this router. So this man in the middle attack, where the suspicious hacker is now convinced these computers, no, just talk to me first. No, they forward it along. So maybe you see this traffic kind of appears normal as humans between the two, but now this potential attacker is actually controlling the data and is able to capture it as they pass it along to do whatever they want to it. Maybe they can alter the data. Maybe they're just saving it, for potentially using it, get sensitive information. All right. So you've explored various ARP broadcasts, but ARP messages can either be broadcast or unicast. Broadcast means like to the wide, like everyone. Unicast means you're sending it to one person, one address. Valid unicast can be used to verify the router is reachable and properly functioning. For example, routers with ARP unicast, who has this? Okay, blah, blah, blah. Malicious users can formulate a fake ARP unicast by sending the opcode 1 to indicate, yeah, you know how opcode 1 was if you remember, opcode 1 is it requesting, right? You just pretend to be someone else. You just pretend that. And that's how we're doing this. In the attack you're about to analyze, the malicious user injects a bogus ARP message onto a host, which falsely associates its MAC address with some other IP address. This ARP poisoning can then be used to implement a denial of service attack or man in the middle, other exploits. All right. So let's see how this works. And we have to customize Wireshark right here. So we're going to go to edit. Going to go to preferences. Now, once you go to columns right up here, and we're going to add some columns. So this is what steps 18 through 22 do. So you're going to go hit this plus button down here. We're going to change this. Going to be SRC MAC address. Looking at the source MAC address right here. And then we're going to change this from number. Double click on it. You go to hardware, source, address, resolved. It's hard to see. I think the top one's resolved and one of them's unresolved. Make sure it say resolved. All right. And then we can actually drag this to right below source. Now I'm going to add a second one on here for destination, doing the same thing. So we're going to go destination MAC address. And I'm going to change this to hardware destination. Resolved right here. I'm going to drag this up to here. Now I'm looking, not the source. Remember before, those were like the source and the destin. This is gonna like how you tell that to validate a few things. Okay. Now that we've put those in here, and did I do anything else? That's it. Hit OK. So notice I now have source MAC, destination, dest MAC up here, and that was through step 27. All right. So this, this is just getting details that are down here, but this will help me like look at things better. And I think we'll probably be future lessons be adding things up here too. Room. Oh, well, we're not using this one. So the man in the middle attack. Recall that the goal of man in the middle is to embed a malicious user between two target devices on a network and intercept their communications. This means that there are two victims. However, capture data, we're only going to see one. So they're simplifying this for us. We're only going to look at one of the, try to make it easier for us to read. So that's what they're doing with this. All right. Assume that you're the system admin. Now, a few things to note here as we go on. Assume you're a system admin of a network whose activity you've been captured in a packet capture file. You suspect there may be a problem with the network and are looking for any suspicious behavior. So you have to, to have it handy, record the details of this router. Remember, your router's IP address is 172.16.0.1. That's what you know it is, okay? And the MAC address is this Cisco thing, all right? What we're going to see in this attack is how those router addresses, this IP and this router should not change. What we're going to see in these attacks is basically they're going to change those. They're going to change those. All right. So that a new router, a new MAC address is now associated with this IP. Let's open up this ARP poisoning capture. I'm going to minimize this. I don't know if it matters if I do or not because I did those changes. This is a new capture with ARP poison. You'll see a lot more packets on here. Ugh. A lot more stuff going on. This unfiltered. Okay. Like how it color codes. Color codes, I think, by protocol down here. So it kind of helps out. All right. So I'll find the first ARP packet. You can use an ARP filter in the info column. Okay. So let's find the first ARP packet. Now, what you can do, you can like look for ARP, or you just type ARP up here. Oops. No. Okay. I have to restart the lab. All right. Saved. Just had to refresh. So type ARP in here and hit enter. And notice it'll filter out all your anything with ARP in it. So our first packet with ARP is packet 54 right here. Let's click on this. Look at the details. Okay, in the info column. So you see ARP is Hewlett Packard, source of this, saying, who has this IP address? 06107. Please tell 172.16.01. Isn't that the router? Like, wait a minute. The router? Not the router, right? That's kind of weird. Why would you tell? Why would so is this person trying to tell the router? Said, who has this one? Please tell the router. But wait, this is a Hewlett Packard. My router is a Cisco. And that's the problem we're going to have here. Why would this guy, when it does a tell, it should say, hey, tell me. But saying, oh no, tell this guy. Who has that address? It's weird. All right, in the info column, who has one tell appears to be a broadcast message. Record the following. What's the source here? Now let's find the source. Oh, the source is right up here. Hewlett P. Hewlett P. So I'm going to go Hewlett. That's like Hewlett Packard's probably computer. That's what it stands for. BF91E. BF91EE. The source MAC address for that is the same thing. Now the destination is going to be this Dell CO. I mean, if you just want to write Dell, that's fine. 56F1. Not going to matter. F0, right? Yeah, you could just write Dell. Honestly, who cares? And the destination MAC address is the same thing. Okay, cool. The packet details pane. Expand the address resolution protocol element. Record the following information. So this was an opcode of request. 1. Sender's MAC address is the HP. Sender's IP address is 16.01. The target MAC address is everything. I'm just going to say zeros. And 172.16.0.107. 0107. Okay, so you look at this information and go, compare what you know about the router to the packet data. Wait a minute. I was told address 01 is the Cisco. But now this guy's saying, hey, I'm 01, but I'm the Hewlett Packard. What? Router is reported the packet is now incorrect. It's reporting that this MAC address is this address. It appears the Hewlett Packard machine is acting like your router. It's pretending to be my router. Whatever this machine is, this Hewlett Packard is pretending to be my router. Next, compare this ARP message to the one you know is legitimate from, okay. Oh, remember the legit one, right? Explore the differences between those. So, what are the differences from back when we did this, the first thing? Explore differences between the legit ARP packet and the one that is ARP poison, which are some additional clues, right? Well, the poison packet, the target MAC address was zeros. This indicates a broadcast address. However, the address conflicts with this destination MAC address. So the target is a broadcast, but the target IP address, it's trying to send it to 07, which is actually some computer, some Dell on the network, right? If we actually look this up, I don't want to make things up. When we did an ARP broadcast before, so this is supposed to be like a broadcast. It's pretending it's a broadcast. And that's like what this thing was doing, was broadcasting. But when it broadcasts, it has this address instead. Destination MAC address in the packet list. Inspect this. Target MAC address is this. So when this did, it did a target MAC address of this and make a broadcast when you have a MAC address of nothing, right? You don't know who to send it to. However, this address conflicts with the destination MAC address. So it's trying to do a target. Okay, so here's the thing. On the legit one, Let's explain that differently. I'm understanding this better now. When I broadcast, my destination MAC address was broadcast, right? When I was sending a broadcast, because I want to ask. And that was the destination up here. And then the target MAC address was 0. Because it's a broadcast. I'm sending out to the whole network. When this one's on here, this is the poison one. They're trying to be a broadcast too. But if you look at the source and destination, the destination is not broadcast. It's I'm trying to pretend I'm a broadcast, but I'm only sending it to this Dell computer right here. So that's what they're trying to do. They're targeting this one computer on the network, pretending they're a broadcast and saying, "Oh, can you just tell me?" So they're not trying to mess with every computer on the network, just targeting one. If they mess with everyone, then it might be more suspicious. So it looks like you're just be a little sneaky. It's going to one specific target, the Dell, to spoof the router's address. So just targeting one computer. Finally, ARP reply to the request. Record the following info. So let's reply to this request. We have this one. And the reply would be right here. The Dell is going to, so it asks who's this, and the Dell says, oh, the IP address is right here. Okay. Then right after this, the Hewlett Packard tells the Dell that one is at that. Ooh. Okay, and then it's just telling me where I am at. Okay. So opcode. Use the info column to see response who has the opcode packet. Notice the HP also sends a confirmation. Our message this is not the reply from the Dell. We're doing this one. So let's do opcode replies as opcode reply. So reply. Sender's MAC address is going to be the Dell. I'm just going to copy from up here. Sender's IP address is 1607. 107. The target MAC address was going to be the Hewlett. And IP address of 1. Okay. What seems strange about the target IP address and the target MAC address? Okay, again, IP address is a router, but the MAC address, that's not my router's MAC. It should be that Cisco. Same thing. All right, the packet numbers for these two things were packets 54 and 55. So this is going to be 54. This one was 55. So packet numbers on this. Next thing. Next steps, you'll try to see whether any information was intercepted by the man in the middle, because your packet analysis, you suspect the Hewlett Packard is the bad person, bad dude, and has spoofed your router IP address, is acting as your router. This allows the host to act as a man in the middle, since the spoof message was sent to Dell as the likely target. From your suspicions, you compare a good communication with the Dell to a bad one. All right. So here's what they're doing. We're going to clear that filter. Okay, we have no filter on anymore. We're looking at everything. Here, any filter you may have, and reorder packets by packet number. Okay, so we're already ordered by packet number. Fine. Make your analysis easier. View only the MAC address of the packet capture. So what we can do is of this packet capture. All right. So we're going to go into preferences, and just, you don't have to, uncheck source and destination. So I'm going to go to edit preferences, and the columns, I'm going to go uncheck source and destination. Let me see these two. Okay. Scroll through the packet list, looking for changes to the communication patterns near the packets. Try to see a glitch or anomaly. Okay, so look at what's going on. We go through this. Let's go around. Notice there's like Dell is communicating with the Cisco router and back and forth. Maybe there's like going to YouTube, Google sites, groups, blog search. How to see their traffic and stuff, right? Then we have this request. Hewlett Packard comes in with this ARP, and then it talks back and forth with this ARP. It does some stuff here, doing a lot of stuff. Then afterwards, you know what's crazy? The Dell is talking to the Hewlett Packard and doing like going to UK Athletics or going to ESPN stuff, USA Today, all like the standard like to website traffic. Now instead of going to the Cisco router, it's talking to the Hewlett Packard. So some magic happened right in here, back and forth, communicated, and then looks like things were updated. So now the Dell just doesn't talk to the router anymore to go out; it talks to the Hewlett Packard. Now that thing is capturing all of the network traffic of that computer, and that's what we're supposed to see in this lesson. So look for any changes. Try to see a glitch. Consider the goal of the ARP poison attack. A man in the middle is trying to intercept communications. So that's what we're trying to see. After this ARP and after it finagles some things in green right here, this is going back and forth. I don't know what it's doing right here exactly. But, and then now, instead of doing, it's just using the Hewlett Packard, the router like it should. Last packet before the glitch, and on the first packet after the glitch. Use packet details to record information below. So I'm not going to do this part, but this is what we're supposed to see. Like kind of what I just explained to you. If you look at these details right here, it's going the Cisco to Dell, Dell to Cisco, and back and forth. You can see the source, MAC address, and destination. Like, well, how can I see source and destination? Because we just told me to hide those. Really weird. You know what I don't get? Why did this lesson have me turn these back on? Oh, okay, so source and destination do IP addresses. Like IP addresses for some of these. So notice the Dell and the Cisco router. I was talking to the router that's at 41. And 41.107. So you know what's interesting? You see it's talking to 41.107, right? Back and forth, source and destination. IP address, right? This is still 41 and 107. But the MAC address has changed. So it's if you looked at just the source and destination IP address, you say, oh, it's still communicating back and forth to the same thing. But no, it's saying because it's now mapped the MAC address to something else. So that's what's being suspect right here. It's sending packets, so it's updated its information, its ARP table that the IP address is now associated with this MAC address. That's why seeing this source, the MAC address, is important instead of just the IP address. Like that's a big thing to get out of this lesson. That if I just look at source and destination, they didn't change. 107 to 141. Just like above. 107 to 141. But the Dell and Cisco's were communicating, and now those are associated with Hewlett Packard and the Dells. That's what you should see. That's what that table's trying to fill out. I don't want to fill it out. How do you protect? So that's the key thing there, and that's why we wanted to add that column to have the MAC address, not just the source and destination IP address. So hopefully you got that. Now, how do you protect against this? This is the final part of the lesson. So a system is the victim of ARP poisoning. Network administrators can clear the ARP caches to generate new ones. Just clear them. Oh, but that comes at a cost because it interrupts the workflow. And you're slowing down the computers. Might interrupt what they're doing, right? So maybe you don't want to do that. But instead of just clearing the cache, and like, how do you know that? That doesn't just change again. So how do I know it doesn't get changed again, right? So instead of this, we can reduce the risk by spoofing or creating a static, non-changing ARP entry in the table. So I can force an entry on the table and say, no, don't change this. Like I can do this as the administrator, say, don't get fooled by another computer saying the address changed. Only trust me. So we're gonna do this. This is one way. It's kind of like a temporary fix until you figure out, like, if you don't know where that computer is, this might be a problem. It's a temporary fix, or it'll prevent it from changing. If so for example, the router is going to be at one IP address. You're not changing it. You might add or remove computers to a network. Their IP addresses might move around. You might be like, but the IP address for the router, that's going to stay the same. So we're going to just say static. It's this IP address, this MAC address. Nothing's changing until you upgrade your actual router hardware to something else. Then you'd have to update this, but no. So what I'm going to do is we're going to copy that line right there. Oh, so you have to ARP-A to see the whole thing. So notice this is my ARP cache, that table thing we're talking about, basically on in a PowerShell. Since I've added this line right here with the -S, the S means static, sending, right? What do the parameters represent? The first parameter is IP address, second is the MAC. The command creates a permanent map, so it's making it static in here. So after I did this command, this internet address, this physical address, static, saying don't change it. And these are dynamic. I mean, we want dynamic things just in case like a new computer comes in the network, or maybe it moves around, like you disconnect it and bring it back. Things can change all the time. Or maybe like, so like on a network, you have this IP address now, but if I remove that computer, a new one comes in, they might take that IP address. But I don't want to keep, I want to let those be dynamic, but certain things I know I'm not changing, I'll make static. So I just added it to the table, and that would be a good temporary fix. Now we're secure. And that's the lesson, folks.